rate of decay, and half-life. Radioactivity has a very definite mathematical description, which allows the rate of decay to be calculated. For example, the population of radioactive nuclei, N, is given by the mathematical expression N equals to N sub 0 e to the power of negative kt, where N sub 0 is the original number of nuclei, and T represents time, and K represents decay rate. The radioactive half-life is defined as the amount of time taken to reduce the number of nuclei by 50%. Mathematically, the half-life can be written in terms of the decay rate, which is half-life equals to ln 2 over k, where k represents the decay rate. But guys, wait! Apparently, the formula of the half-life depends on the order of reaction, where the half-life for the first order of reaction is equals to ln 2 over k, and the half-life for the second order of reaction is equals to 1 over k concentration of A sub 0. This is the example of half-life graph, with y-axis noted as concentration and the x-axis noted as time. As we can see, the total concentration is 1 molarity. Taken 50% of the 1 m is 0.5. The time taken for the concentration to reduce to 0.5 is 1. Moving on, the time taken for the 0.5 to reduce to half of it, which is 0.25, is 2.
The question. A radioactive isotope of cesium has a half-life of 30.8 seconds. If we have a 25-gram sample, we'd like to know how many nuclei are present initially, and after 5 minutes, how many are left? And what is the activity at this time? That is, how many decays per second are there at 5 minutes? We'll start by finding the initial number of nuclei. Now, the atomic mass of this isotope is 124, which implies that there is an Avogadro's number of nuclei, i.e. 6.02 times 10 to the 23 nuclei in 124 grams. That's what that means to have an atomic mass of 124. However, we have 25 grams, not 124, which means that the number of nuclei we will have will be Avogadro's number times the fraction 25 over 124, because that's the fraction that we have when compared to a whole mole. So this is 1.21 times 10 to the 23 nuclei. Now let's find the decay rate. This is the expression which describes radioactive decay. States that the number of nuclei there are at a time t is equal to the number there was initially times e to the minus lambda, where lambda is the decay rate, and t, the time. Now I'll go through how to derive the decay rate once you know the half-life. If we divide both sides by n sub 0, we have this expression. And by definition, the half-life is the time at which the left-hand side, n over n0, is equal to 1/2. That's when half of the original number of nuclei remain. So now it's just a matter of solving for lambda. And in order to do this, we have to take the natural log of both sides. We can rearrange to solve for lambda. We were given the half-life, and we can calculate the natural log of 1/2. This works out to be 0.0225 inverse seconds. Now we prepared to find the number of nuclei remaining after 5 minutes. Once again, we start with this expression, and now we can plug in the initial number of nuclei, which we found. We can plug in the decay rate, lambda, and for the time, we have 5 minutes. There's 60 seconds in a minute, so this is 5 times 60 seconds. And we obtain the number of nuclei. Now let's find the radioactivity at that time. The radioactivity, i.e., the number of decays per second, the change in nuclei per change in time, is equal to lambda, the decay rate, times n, the number of nuclei present at that time. We can plug in the values that we know, and we obtain the decay rate, 3.2 times 10 to the 18 decays per second.
That's all for now. Thank you for lending us your ears. Bye-bye.